Today we're going to start with simulation. Okay, we'll also try to finish with simulation today. So it's mostly going to be a single lecture topic. Okay, so the question is, okay, why am I talking about simulation? So simulation is one of the most useful and commonly used techniques to analyze a production system, okay, or any manufacturing system, to not just analyze the performance or the behavior of a manufacturing system, but also to improve it, right? So because once you build a simulation of something, then you can play around with it, try out different sort of things to improve its performance. Okay, now I myself, in my research, actually use quite a bit of simulation. You can even All of my PhD students are doing simulations of one sort or the other. I publish regularly in the Winter Simulation Conference, which is probably the premier conference dedicated to simulation of various types of systems, especially stochastic simulation, right? And I'll come to that in a little bit. So I have a fair bit of experience with simulation, and as I said, in any system um, that involves humans and people interacting, um, it is and which means that any real world system, most real world systems, um, simulation, there is uncertainty, right? So there's a lot of uncertainty in, for example, the way people interact, how many people come, all these things, which is reflected in uncertainty in things like demand, service, outcomes, etc. So, in order to capture all of this and to model all of this, analytical techniques are almost always not enough, right? So, and that is why you require simulation. So, I work a lot in health, in modeling health systems operations, different aspects of health systems. So, so I've worked in, for example, infectious disease transmission dynamics. I've worked in health operations in healthcare facilities, which I'll describe shortly. I've worked in, for example, developing models of biomedical measurement processes in diagnostics and so on. So, and I can tell you that uncertainty is everywhere, right? In especially in health, um, there's uncertainty of the approach that is used to sort of provide care. There is uncertainty, of course, in the outcome. Just because you treat somebody does not mean they will always become they will get cured, right? COVID, for example, is a perfect example where it's a virus and we can provide some treatment. So, for example, remdesivir is available right now, dexamethasone is available right now, but it does not come with a perfect cure rate, right? So, in order to capture all of this uncertainty, it is essential to have a way of course, modeling this. Now, you can either model it analytically, or you can model it, which means that you can write down equations for it and then maybe solve those equations, or you can model it computationally, right? And computational models of real systems is what we are going to be discussing in this case, um, and is what we're going to be discussing in this lecture. And the computational models of systems that we develop are what we are going to refer to as simulations. Okay, so as I said, it's a widely used tool. So the main thing, so let me actually just sort of define what a simulation is, right? So what is a simulation? Now, a simulation is essentially just a computational model of a system, is a computational model of some system that imitates or mimics some aspects of its behavior. Okay, so you study a system. So, for example, you can study the operations of a clinic, okay, which has maybe like a doctor, it has a couple of nurses, It has maybe two types of patients coming in, and it has some support stuff as well. So a simulation, you can develop a computational model of the provision of care to patients in this system, and that can be a simulation. Now, the simulation that you develop does not need to incorporate every single thing that occurs within that system. It only needs to incorporate the things that are important for the purpose of your analysis. So you have to decide the purpose of your analysis and then figure out what to include in your simulation, right? So that's why I did not write it's a computational model of a system that imitates some aspects of its behavior, not all aspects of its behavior. We'll come to this uh, in more detail later. But in general, it's any computational model of a system that you develop. Okay. Now, keep in mind that I've not yet specified that it's a computational model that incorporates uncertainty or does not incorporate uncertainty, right? So we have not done that. Let's write that down though. So broadly, there are many different ways of classifying simulations. Um, I am going to talk about two simple distinctions first. Okay. So you can have, for example, deterministic and stochastic simulations. Yeah. Okay. So now what is a deterministic simulation? So deterministic simulation is a case where you don't incorporate uncertainty into your model of the system. You assume that everything is fixed. So the question then becomes, okay, if there is no uncertainty, then what is the purpose of a simulation, right? So in many cases, what happens in many physical systems in particular, when you develop models of physical systems, when you develop simulations of physical systems, uh, the you often develop simulations because the mathematics are hard to solve by hand. So you have a large number of maths equations to solve, for example, in order to figure out what the sort of the steady state behavior or the equilibrium behavior or the uh, or whatever end performance measure that you want to measure. In order to get to that point, you have to solve a very large number of equations, right? Or you may have to solve equations in a way that is not possible by hand. So in which case, what you do is you start the simulation at a particular state, and then you solve the equations on the computer to get it from one state to another. Okay. So and the computer itself, and of course you program the computer to solve those equations numerically. Okay, so it might be, for example, that you may have 200 equations that describe the evolution of a system from the starting point to the ending point. Now, you can't you can't solve those questions, you can't solve those equations each time you want to try something different, right? So you program it. So you program the solution, and that uh, the solution of those equations to get to that final state for different values of maybe initial state, for different parameter values, and so on. So in order to do that, and in many cases you may not be able to solve those questions by hand, right? So for example, if you develop some sort of a finite element model, or I mean, there are maybe for a particular set of differential equations that you develop to describe the evolution of the system, you will not be able to solve it by hand, right? Because for example, I developed a model of along with a BTech student, actually we developed a model of TB, of the transmission dynamics of TB. So by the time we were done with the model, we had close to, I think, 50 to 60 differential equations. So I required a set of 50 to 60 differential equations to model how the transmission dynamics of TB, right? And we could not, of course, solve this by hand. So we actually had to feed it to and of course, remember, we had to solve this for each point in time to figure out how the transmission of TB evolves over time, and we were looking at a time period of nearly around 25 years or so, right? Because we had to calibrate to around 15 to, I think, nearly about 15 years of data, and then we wanted to project the evolution of TB after 15 years, after those 15 years, right? So we could not solve 50 sets of differential equations at every single point in time, at every single year. So what we did was we programmed it. So we programmed the model in MATLAB, and then we solved it at each time point to get a sense of what the TB situation looked like in India over those 15 years. So we even published a paper out of it, And for anybody who's interested, uh, I'll be happy to discuss that. Okay. All right. So that is an example of a deterministic solution. We did not incorporate any uncertainty in there because the model was complicated enough as it is. Although later on we did incorporate some uncertainty, that is also there in the paper, but I'll come to that a little later. Okay. But for now, as I said, that is an example of a deterministic simulation. Now, what we are going to deal with in this particular lecture is stochastic simulations. Okay. Now, stochastic is another word for random for the most part. Okay, so that there are specific definitions of, for example, stochastic mathematical statistical definitions of stochastic processes, but I'm not referring to that. I'm referring to the word stochastic in general, okay, or random. So in that general context, stochastic is another word for random. So so now the question is, um, what so now the question is, what is a stochastic simulation? So a stochastic simulation is any simulation where you incorporate random variables. Okay. Now this is not a very formal definition. This is my experience. I think that in my experience, it is sort of the best way to define a stochastic simulation. Any simulation where you model one of the parameters, maybe one of the um, any one of the parameters, any one of the outcomes. If you model any one of the parameters as a random variable, then the outcome will, I think, automatically also become a function of that random variable, and hence it will become a random variable in itself. But in general, any simulation that has a random variable or more in it, it has random variables in it, is a stochastic simulation. And we are going to deal with that because that is the most common type of simulation that is developed in the context of analysis of manufacturing or service systems, right? So stochastic simulations are most common in analysis of manufacturing and service systems. Okay, so what I'm going to do is, so what am I going to present in this lecture? I've told you what a simulation is roughly. I've told you what two simple ways of classifying simulations, and I've talked about the and I've said that we're going to talk about stochastic simulations in particular. So I'm going to show you overall what a simulation can give you. I'm going to walk through the development of a simulation as well. Okay, how do you develop a simulation? And it's not enough once it's okay, program some simulation. You need to, the idea is to program a correct and effective simulation. Okay. I'll talk about what are the things to keep in mind, what are the things to do, what are the steps, the general steps in developing a correct and effective simulation. Now, all of this, I'm not referring to a particular textbook for this. This is just based on, of course, I've read textbooks on simulation. There are excellent textbooks on simulation. Any student who has worked with me on simulation typically knows that I refer them to one or two textbooks usually to get a sense of what simulations are before they start work. But this is the steps that I'm sort of that I'm going to present here are all based on my experience in developing simulations, and also maybe contributing to and also sort of contributing to the process of developing simulations and so on. Okay, so as I said, we are going to be focusing on stochastic simulation. I'll briefly describe um, I'll briefly describe what are the different types of simulations. But one thing to note is, after this, I'm actually going to show you an actual simulation that I've developed in Python of a very simple system. Okay, and I'm going to use that to sort of present the different steps in. I'm going to use that to present the different steps in developing a simulation. Right? Okay. Now. Um, So, what are the different types of stochastic simulations, especially the ones that we are interested in? Okay, so stochastic simulations on whole, I'm going to divide them into four broad categories. Okay, so I'm going to first call the Monte Carlo simulation. Next, you have discrete event simulation. This is the classification that you will come across most often in the industrial engineering operations research literature. And generally, people who analyze manufacturing systems are industrial engineers or mechanical engineers uh, or manufacturing people in general, and they will also be familiar with this sort of classification. Okay, and this classification I think is broad enough that it applies to most different types of stochastic simulations. Monte Carlo, discrete event, agent based. This is a relatively new development, but not so new also. Maybe around 10-15 years back it was first developed. Uh, but now it's become reasonably common. And in fact, I developed a bunch of agent-based simulations, a couple of agent-based simulations myself. Published on that recently, also with undergrads, by the way, from IIT recently. Uh, And what I can tell you about agent-based simulations is, especially now, you will hear the term a lot more because they're some of the most effective ways to model infectious disease transmission dynamics. Okay, especially in the context of COVID-19. So, in fact, one of the models that we have developed, agent-based models that we have developed and are developing. We're still working on that. We've published some initial work on that. Is agent-based simulation of the hepatitis C virus transmission dynamics. Okay. Um, and the final one is what is called a systems dynamics. Okay, so this is not so I would this is not necessarily a um, very old or new type of model. It's been around for some time under different names actually, but it's not very often used in modeling manufacturing systems analysis. So I'm actually going to be focusing on one particular simulation type out of these that is actually by far the most common method simulation type that is used in modeling and analyzing the behavior of manufacturing systems. Okay, so the simulation type, that is the stochastic simulation type that is used most commonly in analyzing and modeling manufacturing system behavior, is actually discrete event simulation. So this is most widely used in manufacturing systems analysis. Okay. Uh, Now, I'll very briefly explain what each of these types of simulations is, because simulations are, because I think it's important for you to know, so that you can then choose actually which type of simulation to develop. Um, and then I think we'll go into discrete event simulation in detail. Okay, but almost all of the steps that I'm actually going to describe in developing an effective simulation, those are applicable to all of these types of simulations. Okay, it's general, but the specific type that I'm going to talk about, that I'm going to present and I'm going to talk about, are discrete event simulations. Okay, so there are many different things that one can say about simulations. There are many different things to understand when developing a simulation, when studying simulations, and so on, when learning about simulations. In fact, one of the things I would like to do, I think sometime in the near future, actually, hopefully maybe in the next or the semester after the next, is to actually develop an elective course on simulation design and analysis. Okay, and in that, yeah. So and then, but uh, so there is enough material for a semester long course as far as simulation design and analysis goes. So, and we have only about maybe a max of about a couple of lectures on this. So keep in mind that I'm going to go through. I'm just presenting you with an overview. Okay, of what simulations are. All right. So let's actually talk about what each of these simulation types are. Let's talk about Monte Carlo simulation first. Okay. So my entire PhD thesis was using Monte Carlo simulations. So you can say that I have some familiarity with it. Uh, and they are also very most often used, I would say, in physics, in not just in physics, in finance, uh, in wherever I think physical chemistry, where you're modeling actual physical systems, and you want to understand how it behaves under uncertainty, very often you use some form of Monte Carlo simulation. Secondly, the definition of Monte Carlo simulation is also, it's kind of broad. Okay, uh, it's one of those things where there isn't a very clear definition of what a simulation, what a Monte Carlo simulation is. But that said, the definition that I am going to present you is broad enough that you can even think of it as covering all these other types of simulations, like discrete event, agent based, and system dynamics can also come under. Okay, so let me give you the basic definition of Monte Carlo simulation. So the basic idea is this: let's say that you have some system Y. Okay, you have some system that is described by this model. So Y is a function of x1, x2 through xn. Okay, let's for now assume that YF is a map from Rn to R, although this is not strictly necessary. You can have a a multidimensional function as well, a multiple valued function. But for now, for simplicity, let's assume that f is a map from Rn to R. Okay, it's a single valued function. Now, a Monte Carlo simulation is one where you use a Monte Carlo simulation when you cannot estimate y directly as a function of x. Okay, in the sense that, and I'll explain what that means. Now, let's say, for example, that uh, your x1, x2, up to your xn are all random variables. Okay, so each of them has some distribution. We'll call this, let's say, g1 of x1, g2 of x2, up to gn of xn. They have some PDF. Okay, so let's assume they have some CDFs. Okay, because PDFs are specific to continuous variables. There's no reason why all of them have to be continuous variables or discrete variables. They can be a mix. That's perfectly fine, or they can all be discrete or all be continuous, right? Let's say that G1, X1, G2, X2 through Gn, Xn are the cumulative distribution functions of X1, X2 through Xn. All right. Now, typically, when you have a function, so let's say you're dealing with a simple function, y is equal to ax1 plus bx2. Let's assume that x1 and x2 are normal random variables. Okay, so you'll have some n of they're described by two normal random distributions. So x1 is described by the normal random variable n1 with some mu1 and sigma 1 squared. X2 is described by some normal distribution n2, which is described by its mean and standard deviation mu2 and sigma 2 squared. Let's assume that the x1 and x2 are both independent random variables. In such a situation, and given that this is a simple linear combination of two uncorrelated normal random variables, you can easily estimate what the distribution of y is. Analytically, you can figure out what the distribution of y is, right? It's also a normal random variable with uh, mean being a into expected value of x1 plus b into expected value of x2, with variance being a squared into variance of x1 plus b squared into variance of x2, right? Now, what if, and the reason you can do this sort of combination is because n1 and n2 are both normally, x1 and x2 are both normally distributed, they're uncorrelated, and they're combined in a simple way. They're simple linear combinations, right? What if what if f was complex? Okay, and the distributions of the x1 through x1 were also, it doesn't necessarily need to be complex, but let's say, for example, you had a mix of you had a mix of discrete and continuous random variables. Okay, so f is complex. So let me give you an example of a complex function that is not so easy to analyze. One that we actually work with is, let's say that f is a logistic map. Okay, so f is a logistic map. Now, what does that mean? So it means that, let's say that f of x, and here I'm going to refer to x as a vector, can be written as 1 by 1 plus e raised to minus, I'm going to write this as beta transpose x. Okay. So in this case, x is a and let's say that the and so x is in Rn. Okay, and let's say that x can, for example, be a mixture of continuous and discrete random variables very different with very different with very different distributions. So one can be exponential, binomial, normal, gamma, beta, whatever, right? So in this situation, figuring out what the distribution of y is, right, which is a function of these random variables, that is not so easy. So analytically, it is not easy to figure out what the distribution of y is. In such a situation, you use what is called as Monte Carlo simulation. Okay, so what you do is this. Now, you sample from the distributions of each of x's. Okay, so what you do is you create one sample of x. So for example, you get a value of x1 1, get a value of x2 of x1, you get a value of x2, you get a value of x3 from the distributions. You sample from the distributions and you create a one sample for x as a whole, okay, by sampling from their individual distributions. After you do this, you plug it into f. Okay, now I'll come to the case where actually sometimes it's not so easy to plug it into f either, but for now let's assume that you sample from these distributions and you plug it into f. And for this particular sample of x, which consists of samples of x1, x2, x3 up to xn, and in such a situation x is called as a as a random vector, okay, because each of its components is a random variable. So each of its components is a random variable, is a random variable. You get one value of y. Okay, so what have you done? You've sampled from the distributions of x1, x2, x3 to xn. You've created one sample of the random vector x by putting them together, right, as the components of x, as the components of a vector. You plug it into f and you get the value of y. Okay, and beta, by the way, here is just a set of coefficients for that function. It's a set of parameters for the function. Similarly, you create another y2 as x12, x22, x32, and so on up to xn2. And then you get another value of y2. So you do this a large number of times and you get x, let's say you do it m times, right? So m times, so you get x1m, x2m, x3m up to xnm. And you get the value of y1, y2 through ym. Now, what essentially do you have? You essentially have a large number of values of y1 through ym, and these are essentially samples from the distribution of ym which you don't know at this point, which you have constructed used by sampling from the distributions of uh, x1 through xn and plugging it into f. Okay, now once you have these values of y1 through y1, y2 through ym, you can actually plot a histogram. You can conduct statistical tests to figure out what the distribution of y is. Okay, so this entire process is called as a Monte Carlo simulation. So the Monte Carlo simulation is used when you do not have a when it is not easy to characterize the distribution of some output of some function which is of the output of a system which is represented as a function of some input of which is represented as a function of some random variables. Okay, so once again, Monte Carlo simulation is used when it is not analytically easy to characterize the distribution of the output of a function of random variables. Okay, in such a situation, what you do is you generate a large number of samples of um, large number of samples from the distributions of the input variables. You plug them into the function, you generate a large number of samples of the output measure, and then you numerically, statistically, you figure out what the distribution is. All right. Okay. Now, so this is what a Monte Carlo simulation is. How is this used in finance, for example? Okay. So in finance, one of the things that you do is you may want to construct a portfolio. Okay. So let's say that you have 1 lakh rupees, and let's say that you have 1 lakh rupees, right? So this is your budget. And let's say that there are n stocks that you're considering. Let's say that there are n stocks. So the question now is, how do you, what is the question is, how should you invest your budget of 1 lakh rupees in n stocks such that you maximize your returns at the end of your investment period? Okay, so let's say I'm investing today and I want to see what my returns are going to be like 1 week from now. Okay, so so the question is, let's say there are 10 stocks. Should I invest all of my 1 lakh rupees in that 10 in those 10 stocks? Should I invest maybe 20,000 in one stock, 5,000 in another stock, 6,000 in another, and so on, right? So what is the optimal allocation of my stock? So that is the first thing to figure out. And this is a very, very standard problem in finance called as portfolio selection or portfolio optimization. Okay. So what is the optimal portfolio that you can construct from given a set of stocks and a budget? Okay. So in this scenario, what one of the things that you can do is you can model, you can figure out, you can analyze stock data. You can analyze weekly changes in stock prices over a long period of time. Okay, for each of your n stocks. So for each of your n stocks, you get historical data for weekly returns. What do I mean by returns? So for example, let's say that stock prices change by okay, let's say stock prices change by 10% in 1 week, right? For a particular stock, maybe in the next week it changed by minus 3%, and then in the next week it changed by minus. So those percentage values, for example, can be the returns. So you get historical data for weekly returns for each stock. You can fit a distribution to weekly returns for each stock. And then what you can do is, let's say, for example, I have one particular allocation, which is W1, W2 to WN. So the W here represents the fraction of my budget that I have invested in the first stock. Okay. So W is the, let's call WI. All right. So let me just write this a bit more clearly. Fraction of stock invested in, fraction of budget, sorry, invested in stock I. Okay. Now, of course, your sigma I WI needs to add up to 1. Okay. So what you can do is you can take a particular allocation W1, okay, W1, W2 through WN. And then what you can do is you can then model the average returns from this portfolio. So what we need to decide are the optimal values of your W1, W2 through WN, right? So for a given W1, what you can do is you can simulate is for a given W1, you can actually sample a large number of distributions, the large number of samples of the returns from each stock. Okay, so for example, let's say you can actually generate, and for so for example, let's take a particular allocation W1 through W1, W2 through WN. Okay, now let's actually denote the returns by for each stock as R1, R2 through Rn. Now what we can do is we can generate, this is return 1, first sample, so let's call this R1. Okay, so I'm going to call this R1 is a vector of R11, R22. What is this? R1 is a vector of returns that you have sampled from the distributions of the weekly returns that we have figured out here. Okay, for these returns, you can actually apply this. You can apply this portfolio, and then you can figure out what your budget is, what your returns are. Okay, now obviously, so what will be your actual? Let's call it your stock value. Let's call the stock value corresponding to 1 is going to be, let's call this W, is going to be W transpose R1. This is going to be the actual stock value after 1 week for this allocation, for this sample of returns. Okay. Similarly, what you can do is you can generate from the distribution uh, of the returns, you can generate a large number of values of R. So you can generate R2, which is going to be R2, R, sorry, this. You can generate R12, R22, R3, Rn2. All right. And similarly, Rm, which is R1m, R2m, R3m, up to Rnm. For each one of them, you can actually also calculate the corresponding S2, which is equal to W transpose R2, Sm, which is W transpose Rm. Okay. Then what you can do is you can calculate the average stock value for this allocation, for this particular portfolio that you have generated. So when you say portfolio, we just mean what proportion of money, what proportion of stock, what proportion of your money you've invested in a given stock. Okay, so this is in some sense the portfolio. So if you, for example, if your WN is 0, it means you don't hold any of this stock at all. And if, for example, everything else is 0 but your W1 is equal to 1, it means that you only purchase stock 1, right? So the average stock value for this portfolio as a function of W can be written as just the me is I equals 1 to M, 1 by M, Si. All right. So this is the average stock value W for a given portfolio. Now, the question is, how does this help in finding the optimal portfolio? Okay. So so what we have done is we've conducted a Monte Carlo simulation for a given portfolio W1, W2 through Wn, using by sampling returns from the distributions that we have estimated from historical data, and using that we figured out what the average stock value is going to be after 1 week. Okay, for one portfolio. Now if W1, W2, so each of your Wi can lie between 0 to 1, right? Because they represent fractions. So for all I. Now, which means that there are there are an uncountably infinite number of Ws, right? So what you can do instead is, now obviously we can't conduct a Monte Carlo simulation for an uncountably infinite number of times. So what you do in that case is you can maybe evaluate, for example, 1 lakh different portfolios. So running this simulation typically takes a very small amount of time, right? And if you're a if you're a finance company, then you generally have a very strong high performance computing cluster, and that is set up to do algorithmic trading and all these kinds of things. So running a simulation like this for them is, is nothing. This will take seconds, not even that much actually. So in this situation, what you do is you can simulate a large number of you can conduct a large number of Monte Carlo simulations. uh, you can conduct a large number of such simulations for millions of portfolios. So for example, let's say we take 1 million portfolio. Okay, so for W1, let's say, so 1 million portfolios, you can actually, your W can range from 1 to 1 million. Okay, and for each of these, for each WI, you get a S, you get a S bar. Okay, so you get an average stock value. This I'm going to call SY. For So for each W, you get an S bar. Okay, and what you can do is from these, you can find what is the select the max. So select the W that gives you the maximum stock value. You can select the W that gives you the maximum stock value. Okay, so that's it. So this, and then you can go with that particular allocation. Of course, is this an actual optimization? Have we actually performed an optimization problem? No, we have not. There is actually a Markowitz. There's a proper optimization framework for this, which was introduced in the 1950s, called the Markowitz. Called the Markowitz optimal portfolio selection framework, which in fact we're working on some research related to that right now. Uh, but as I said, this is the way to this is one way to apply Monte Carlo simulation. So in actual, in a lot of finance companies, when the portfolio selection process is actually quite complicated, when you for example, you cannot actually the Markowitz framework, by the way, is a simple it's a quadratic programming problem actually that can be solved quite easily. But in many cases, you can't apply that directly. Instead, what you do is you apply something much more. Um, you have a much more complicated sort of mathematical framework. In such situations, it's not so easy to solve it directly. So instead, what you do is you conduct these Monte Carlo simulations in this way and find the and then go with the portfolio that maximizes your stock value at the end of your period of investment. Okay, so now this is an example of Monte Carlo simulation. Okay, I know that I've almost taken 45 minutes to explain this, but this is important because I think it is useful for you to know. Uh, it is useful for you to know what Monte Carlo simulation is in general, because as I said, a lot of you might be going to analytics jobs, and you will be using Monte Carlo simulation, and there's a good chance that you'll be using some form of Monte Carlo simulation to evaluate. If nothing else, you might develop a model, and then you want to know how sensitive is your model to uncertainty in its parameters. In that case, you characterize the uncertainty in your parameters by some distribution, and then you use Monte Carlo simulation to figure out what the average outcome is with respect to the uncertainty in your uncertainty in your parameters of your model. Okay, so now I hope this was useful to understand what Monte Carlo simulation is. I'm going to very briefly explain what agent-based simulation is. I'm going to leave discrete event simulation for the next lecture. Okay, and where I will go through it. I'll present a simulation in detail, um, a presentation simulation in detail, and I'll describe the general steps for developing a simulation also in some detail. Now, what is agent-based simulation? An agent-based simulation is one where you are interested in how given a set of entities, right, uh, called agents, let's say, given a set of entities called agents, you are interested in modeling their interactions. So, for example, one agent interacts with another agent who may interact with a large number of agents. So, there is some interaction pattern that you actually model between agents, and you're interested in seeing how what is the collective behavior that emergence, or what is the phenomenon that emerges as a result of these interactions. And these interactions are typically modeled as probabilistic. As I said, agent-based simulation is a term that you will hear widely with respect to, especially with respect to, for example, modeling transmission dynamics. Why is that? Let me give you an example. I'll take the example of the transmission model that we developed for hepatitis C. Right now, what is hepatitis C? It's an infectious disease of the liver, okay, that you get from a virus. By the way, very different disease from, for example, the coronavirus. The coronavirus comes and goes. In it, you get it. It passes in it, one way or the other. You sort of know the outcome in about 14 days, right? The In about 14 to 21 days. Now, the HCV is a different disease. It comes in. It takes a long time. It infects the liver. It takes a long time. In fact, it takes years, sometimes 8 to 10 years, before you sort of start showing the effects of the disease, actually, noticeable effects of the disease. And by then, sometimes your liver function has deteriorated. And then I think sometimes people get transplants of the liver. They get treatment, of course. Now you have good treatment for HCV. Uh, and usually, as I said, the life expectancy with HCV, for example, is almost around 30 years or so. So you don't. So let's say you get infected. Let's say a person gets infected at the age of 25, then you um, then the person actually lives for an average of around 30 years from there, right? Whereas I think without HCV, the person would have lived the average. I think the life expectancy in India for is around end of 70, is around 70 years or so, right? So it does curtail life expectancy by quite a bit, depending upon when you're infected. Uh, and that has a somewhat high variance also by this 30-year mark. So your disease could progress rapidly depending upon your immunity levels and so on, and other conditions that you may have. Or for a otherwise healthy person, it takes around 30 years. So, and it's an infectious disease. What does it mean? People can pass the disease to each other, so through their interaction. So one of the ways that HCV spreads, it's a bloodborne disease, okay, is through injecting drug use. So a bunch of let's say a bunch of injecting drug users get together and share needles, right? So that is one way. And they're not sterilized needles, of course. So that is one way that the disease can spread. Okay, so one of the reasons why we studied HCV is because the prevalence of HCV in, for example, Punjab and Haryana is quite high, uh, because of because, well, there are many reasons, but one of the reasons is increased in injecting drug use as well. Okay, and for example, I think you may have seen the movie Udta Punjab, right? So in Udta Punjab, you will see that which talks about increased drug use in for Punjab and Haryana, for example. So one of the consequences of that is an increase in, for example, AIDS, an increase uh, in HCV as well. Okay, so so in some sense, HCV and HIV are actually somewhat similar. In fact, very often, not very often actually, but a good proportion of HCV people also have HIV and vice versa. Okay, so the infectious disease model that we developed for transmission of HCV, that can actually be used for HIV as well with some modifications. So in such a situation, what you want to model is the interactions of people, okay, and you want to see as a whole, due to these interactions between groups of people who are of interest to us. In our case, injecting drug users, and other types of people also. But I'm going to just stick to the example of injecting drug users. What is the population level prevalence of? How does the population level prevalence of the disease, that is the number of people who have the disease, change with uh, changes in behavioral patterns? So if, for example, we create some sort of counseling program for injecting drug users, so not share needles, or we actually provide them with clean needles for injecting drug use. And so the question now becomes, why would you want to provide needles, right, to addicts? Aren't you enabling them? Yes, you are enabling them, but the idea is you're at least enabling healthy injecting drug use behavior. Okay, so there's a separate argument about this. Is called as actually needle substitution programs. It's actually been implemented with varying degrees of success in different parts of the world, uh, and people are actually experimenting with it even in India. So what I'm trying to say is, uh, in this situation, if we incorporate this sort of this intervention, which is we introduce some sort of a needle substitution program, how will that affect the population prevalence of um, HCV? Because what we are actually how will that affect the population level prevalence of HCV? Because what we are modeling is a individual level intervention. We want to see what the population level impact of that is, and using that, and we use agent based simulation to actually study these things. So agent based simulation, or ABS, used to study impact of individual level interventions on population outcomes. Okay, this necessarily has to be stochastic, because today, for example, an injecting drug user might share needles, tomorrow they may not, so there needs to be some probability associated with this interaction, right? Or today injecting drug user may, and let's say you start a needle substitution program, not every injecting drug user is going to follow it, so there needs to be some probability associated with whether they follow the program or not, right? So that's where the stochasticity comes in, the randomness comes in the interactions between people, and we model the population level outcomes of this behavior. Okay, so I'm going to stop here. I'm going to continue with discrete event simulation in the next. Systems dynamics, I'm not going to explore in too much detail because it's not used too much. By the way, agent-based simulation is not used only in health. It's also used, for example, in marketing, right? In fact, reasonably widely. So I have a friend in IIM Bangalore who's used agent-based simulation to model how, for example, influencers on influencers actually um, affect the people who sort of view their Instagram pages or whatever it is, right? So it's a very interesting topic. I am personally also very interested in agent-based simulation. As I said, I'm working on it myself, and we've actually, as part of this project, to develop some new methods for using agent-based simulation with a long-term sort of to model long-term behaviors and so on. But anyway, I'm not going to go into the detail of that. But I hope I've given you a good idea of what agent-based simulation and Monte Carlo simulations are. In the next class, we'll talk about discrete event simulations and give you an example of a service system that we have modeled. Okay. All right. Yeah. Thank you.